All right, welcome back, everybody. Today we're going to be talking about section 3.4a, which is exponential equations. Your objective is that you will be able to solve exponential equations today. So, a couple strategies that we are going to be using when we try to solve exponential equations. Change the base of both functions and get them to be the same. That's sometimes possible, that's sometimes not possible. Step number 2, isolate the variable and then take the log or natural log of both sides. So kind of two different approaches, and we'll see kind of what they look like here in a moment. Now, the one-to-one property of exponential functions says that if b to the n is equal to b to the m, then n has to be equal to m. This is kind of a unique thing about it. If you have two things that have the same base, both of these are base b, and they have different exponents, the only way that can happen is if the two exponents are, in fact, equal to one another, right? So if I have 4 to the third is equal to 4 to the x, since these have the same base, they're both 4. The only way this can be true is if the exponents are the same, which means x has to equal 3 in this problem. So here we get to our first problem. In these first couple of problems, we're going to be able to rewrite stuff in the same base. So coming over here, so 16, for example, sometimes calculator is really helpful to this if you think this is a possibility. Really, I think a lot of this comes down to your ability to recognize numbers. So 2 to the third is 8, 2 to the fourth is 16. So that means I can rewrite 16 as 2 to the fourth. So I'm going to have 2 to the fourth over here, and this will be 3x minus 8. Now, right now, what I've done is I've rewritten this so that I have two things that have the same base. The only way that can possibly be true, since these are one-to-one, is that this exponent has to be equal to this exponent. So I can set up a new equation. 3x minus 8 is equal to 4, right? It's the first exponent equal to the second, and then I can solve, of course. So I'll get 3x is equal to 12, which means x is going to equal 4. So x is the value that will make those two expressions equal to one another. Looking down here at this next one again, either you're going to see it or you're not, but 64 is actually, I believe, 2 to the 6th. 2 to the 6th is 64, so I could really rewrite 64 as 2 to the 6th. Now, there is the exponent up here, so that's just going to kind of hang out and actually get multiplied here. Now, looking at 32, 32 actually ends up being 2 to the 5th, and this really comes down to knowing your numbers. If you don't know these numbers, I will give you another way to look at this in a minute. So I could rewrite 32 as 2 to the 5th, and then that's going to be times 2 plus x. Now, this is a quantity, so we're going to put parentheses around it because the 5 is going to have to go to both. In this problem, I've rewritten it in such a way that the two bases are the same, which means my exponents have to really be equal to one another. So I can set up a new equation where 6 times 3x is equal to 5 times 2 plus x. Now, in order to solve this, we, of course, want to simplify first, so I'll get 18x here, and then I'll get 10 plus 5x, regrouping my x's on the same side. I'll get 13x is equal to 10, which means x is really equal to 10/13. Now, that seems like a unique number, but we are solving exponential expressions. We're not always guaranteed to get nice answers. Now, one of the nice things about this is we can actually check our work here. If I actually take 64 and I raise it to the 3 times 10 over 13 power, this is the number that I get. Looking at the other expression, if I take 32 and I raise it to the 2 plus, now let's make sure I get this, yep, we should be fine, 2 plus 10 over 13. I should get the exact same number over here, right? Because that is the number that's going to make these two expressions equal to one another. So you can actually check your work on all of these just by simply going through and plugging it in. Now, if it is not easily or possible to rewrite using the same bases, or if you just don't even realize two things are the same bases, then another way to do this is to take the log with base b of both sides. Here's what I mean by that. So if I come over here and I look at these expressions, you can either take the log or you can actually take the natural log of both sides. Now, in math, we know this to be true. If I take the natural log of both sides, right? If I do something to one side of the equation, I have to do it to the other to keep them balanced. Now, by doing this, the nice part is I know that this x actually is going to slide down in front. So I'm going to have x times the natural log of 2 is equal to the natural log of 7. Now, coming over here, I want to get x alone. That's my game here. So, well, if it's hooked on by multiplication, then I can divide it off using division. Again, to keep it balanced, we got to do it to both sides. And when I do this, I'm going to just be left with whatever x is. So x is equal to the natural log of 7 divided by the natural log of 2. So let's punch that in for a second. Natural log of 7 divided by the natural log of 2, and we get this decimal, 2.80735. 2.80735. Now, remember what this says. We should be able to plug this back in. So if I take 2 to that power, I should get an answer of 7. So 2 to the power that I just found, I'm just going to grab it. And when I hit enter, I should get 7, and I do, which means I found the right answer for the x that needs to make that true. Same thing over here. If I can't rewrite those in the same base, just take the natural log of both sides. Now, of course, the x drops down in front, so I'm going to have x times the natural log of 4 is equal to the natural log of 15, dividing both sides by the natural log of 4. These two pieces will cancel out, so I'll be left with x is equal to whatever this is. So the natural log of 15 divided by the natural log of 4 gives me an answer of 1.95344. Now again, if I just punch that in, I should be able to check this. So if I take 4 to that power, 4 to the power I just found, that should be equal to 15, and in fact it is. So that is how we solve when we get things that don't have the same base. Now this will work even if you could rewrite them in the same base. And this is what I mean by that. In this problem, I could solve this using the first method because 25 is 5 squared and 125 is 5 to the third. So let's do it that way first to show we actually do get the same numbers. So if I can rewrite this as 5 squared, I can rewrite this whole expression as 2 times 2x minus 3 is equal to 5 to the third. Since these have the same base, the exponents must in fact be equal. So I can set up a new equation, 2 times 2x minus 3 is equal to 3. Distribute it out, we get 4x minus 6 is equal to 3, and then solve. Add 6 to both sides. I get 4x is equal to 9, which means x is equal to 9 halves. Now, if I were to solve that using my new method, I would disregard the fact I can rewrite those, and I would take the natural log of both sides to start. So doing so, I would have the natural log of 25 to the 2x minus 3, and that's going to be equal to the natural log of 125. Now again, your exponent always slides down in front. So 2x minus 3, that's a quantity, so I'm going to put it in parentheses, times the natural log of 25 is equal to the natural log of 125. Now we want to get the x alone, so let's divide off that natural log. These two pieces cancel off. Now I can't reduce anything over here. Those are just, that's going to be a decimal altogether. You definitely can't reduce the 25 and the 125. But in order to solve this, I would have 2x minus 3 is equal to the natural log of 125 divided by the natural log of 25. So to solve this, I would come over here and say, well, I need to add 3 to both sides. So I just added 3. This is gone. And then I would need to divide both sides by 2 in order to get x alone. Now we got to be kind of careful how we enter this all in, but this is what x is equal to. So if I take the natural log of 125, and I'm just going to start by only doing this part right now. The natural log of 125 divided by the natural log of 25, I get 1.5 plus 3 divided by 2. I just kind of take it in parts, and I get 2.25. And it turns out 2.25 is the exact same thing as 9 divided by 2. No, it is not. What went wrong? Added 3 divided by 2. Log of 125 divided by log of 25. Where am I off? Answer plus 3. Sorry, 1 second. So something's off here. So let's just go back to the drawing board here. I don't even know where I made my mistake. So I'm just going to shrink all this down. Maybe. Okay, I'm not going to shrink it all down. I'm just going to move it all down for a second. So coming over here, if I wanted to do this, I have the natural log of 20, or 25 to the 2x minus 3 is equal to that. Actually, I wonder if my answer is correct. Let's punch this in for a second. So if I came over here, 25 to the 2 times 2.25, and then minus 3 from that is 125. So actually this, okay, so kind of unique here, is the correct answer. I made my mistake over here. So coming over here, let's recheck this for a second. So coming over here, when I did my work, 25, I could rewrite that as, I'm just going to scribble all this out because this is where I went wrong. Oh, I got it. I'm sure you guys caught it right away. This needs to be divided by 4 on both sides. So this should be a 4 on the bottom. 9 divided by 4 is 2.25. So x equals 2.25. Sorry. I had to find my mistake there, otherwise that was going to drive me nuts. So again, 2 different ways to solve the problem. Personally, I think most kids gravitate towards this idea, so that's what I'm going to be kind of mainly showing you right now. So looking at this next one, again, these can be written in the same base. I'm just going to start by doing the natural log. So if I take the natural log of both sides, I'm going to have the natural log of 27. I'm going to pull that exponent down in front right away. So I'm going to have x plus 3, that's a quantity, times that, right? And then on the other side, I'm going to take the natural log of that, and I'm also going to pull my exponent down in front. So I'm going to have x minus 1, again, that's a quantity, times the natural log of 9. Now, coming over there, we're going to divide off the natural log of 27 on both sides. Actually, so this one, looking at this problem, this would be really hard to solve this way, and here's why. So since I have an x in both of the exponents right now, this is going to actually turn into be a really difficult problem to actually solve. So instead, I think this would actually be the one time where I would suggest trying to rewrite them in terms of their bases. So 27 would be 3 to the third. So I can rewrite that like that. 9 would be 3 to the second. So I'm going to have my x plus 3 that tacks on there, and my x minus 1 that tacks on there. 2 things have been written in the same base that are equal, so the exponents must be equal. So I'm going to have 3 times x plus 3 is equal to 2 times x minus 1. Distribute, distribute, 3x plus 9. Distribute, distribute, 2x minus 2. Now let's just solve. Minus 2x from both sides. I think this is definitely the easier approach for this problem. So I'll get x plus 9 is equal to a negative 2. Subtracting 9 from both sides, I end up with x is equal to negative 11. Right? So again, you can come over there and you can punch that in just by coming and saying 27 to the negative 11 plus 3, getting your number, there's my number, and then 9 to the negative 11, take away 1, should equal that exact same number, and that's how I know I got my answer correct. So let's look at a few more problems here. It looks like we actually have quite a few examples. I don't know that I'm going to cover all of those. So this one says solve for x. So again, the way I would tell you to start the problem is, especially if you only see one x, I would tell you to just take the natural log of both sides right away. This x, of course, is going to drop in front, so it's going to show up right there. Now I'm going to divide off the natural log of 3 on both sides, and that will leave x alone. So the natural log of 21 divided by the natural log of 3 will give me my answer of 2.77. I'm just going to, 124. I'm just going to give 5 spaces after the decimal if I'm not told anything else. And we're done. Just like that. So moving on to the next problem. Now again, we only see the 1x, so we're going to use that same method. One additional piece is this 5. So first thing we're going to do is let's get rid of the 5. So we're going to subtract 5 from both sides. So I'm going to have 5 to the 3x minus 6 is equal to 120. Now I'm going to take the natural log of both sides, meaning my exponent will drop down. So I'm going to have 3x minus 6 times the natural log of 5 is equal to the natural log of 120. Divide off the natural log of 5 on both sides. These two cancel out. So I'm going to be left with 3x minus 6 is equal to, now the natural log, well, hold on, let's not even get the number. Let's do the number at the very end. So I'm going to keep this as the natural log of 120 over the natural log of 5. To solve this, I need to move the 6 over, so I'm going to add 6 to both sides. That will make this disappear. And then I'm going to come over here and divide by 3 to get x alone. So dividing both sides by 3 will tell me what x equals. So to punch this in, I'm going to start by just doing this part first. So natural log of 120 divided by the natural log of 5. That's my number. I'm going to add 6 to that number, and then I'm going to take that number and divide it by 3. So I get x equals 2.9915, and it looks like 5 if I round that fifth spot there. Now, again, it's very important to check your work here. It's easy to check your work, so I don't know why you wouldn't. So 5 to the that power, or I guess I should say 3 times x. This is what x was. And then we are taking 6 away from that. I'm just plugging it back into my original. And then if I take and I add 5 to that whole expression, I should get 125. And you can just see a little bit of rounding error as to why that 0.000002 is there. But we did it correct. Here's another problem where we have an e, right? So that's definitely unique, so you're definitely going to see that one. So again, I would start by just taking the natural log of both sides. Your exponent is going to drop down in front. That's a quantity, so I'm going to put parentheses. So this is the natural log of e and the natural log of 25. One of the nice things about this expression, and we'll see it periodically, whenever you take the natural log of e, you can actually do it on your calculator. So you do your natural log, and then e is a second function. And since there is no exponent, you just assume it's e to the first. And it turns out when you actually punch all of this in and hit enter, you get 1. And anything times 1 doesn't matter. So essentially, the ln of e just cancels itself out, which makes our life actually really easy, because then we're just left with x minus 7 is equal to the natural log of 25. So to solve this, we just need to figure out the natural log of 25 and add 7 to it. So natural log of 25, remember, close that parenthesis, and then add 7 to get your number. So x is equal to 10.21886, or 888. 21888, because the 5 rounds up that 7, leaving this as our answer. Looking at this next one here. Now, when you see this, one thing that you need to deal with first is this 2. It's hooked on by multiplication, so we are going to divide off the 2 to start. These two cancel out, so I'm going to be e to the x minus 2 is equal to 7. Now we're going to take the natural log of both sides. So taking the natural log of both sides, this is going to drop down in front, so I'm going to get x minus 2 times the natural log of e is equal to the natural log of 7. Natural log of e, just like before, cancels out. So I'm just left with x minus 2 is equal to the natural log of 7. Adding 2 to both sides, I'm going to get x is equal to the natural log of 7 plus 2. So let's evaluate that. Second, or natural log of 7 plus 2 gives us 3.94591. Now, again, you can check that really easy, folks, just by coming to your calculator and typing in kind of the original expression. 2, second, e. And then now I got my x right there, so I'm going to grab it. And I want to take 2 away from that. And this should equal darn near 14 exactly, and we can see that that happened, which is how we know we got our problem correct. Now, looking at this next one here, this is where things start to get a little bit more complicated for us. So when we come over here and we try to solve this, again, you're going to take the natural log of both sides to start. Now, when you do that, my exponent's going to drop down in front in both of these situations. So I'm going to have x minus 2 is equal to the natural log, times the natural log of 5 is equal to 2x plus 3 times the natural log of 4. ln of 4. Okay. So when I come over here and I want to solve this, obviously the name of the game is to get your x's onto the same side. There's a lot going on here, so here's how I think I would start this problem. I would first come over here and start by dividing both by the natural log of 5 to get these two to cancel. Okay, now once I do that, that cancels out. That'll be good. I'll be left with x minus 2 is equal to 2x plus 3 times the natural log of 4 divided by the natural log of 5. Now, I think the way I would evaluate this, we definitely have some distributing that needs to happen up top. That's kind of what makes this problem a little bit harder. So I think what I would do is let's actually evaluate this right now. So the natural log of 4 is this, right? So I'm going to take this times 2 to distribute. So I'm going to get 2.77259 x's. And then I need to distribute it. So we distributed it there. Now I'm going to distribute it here. So I'm going to take the natural log of 4, and I'm going to multiply that by 3. And I'm going to get positive 4.15888. And this is all being divided by the natural log of 5. So let's divide it. Remember, that means this divided by the natural log of 5 and this divided by the natural log of 5. So coming over here, 2 points. We've got to be very careful with our numbers here. Actually, I think I can just grab that number right up here. So here's that 2.7259. I'm just going to grab the full. I'm going to divide that by the natural log of 5. So there's the natural log of 5. So when I divide that out, I get 1.7227 it looks like, rounds up, x's. And then if I take that 4.15888 and I divide that by the natural log of 5, I get 2.58406. Now all of this is equal to just x minus 2. So solving this, let's get my x's on the same side. So I'm going to subtract 1x from both sides. Doing so, these two will cancel off. So I'll be at negative 2 is equal to 0.72271 x's. And then at the same time, I think I'm going to, well, let's just leave this. So 0.25846. And then just dividing off that 0.258406 or subtracting it, we're going to end up with, so negative 2 minus 2.28406. We get a negative, that makes sense. Negative 4.28406 is equal to running out of space here, 0.72271x. 0.72271 x's. So last but not least, we just need to get x alone. So we're going to just divide off by this 0.722. 722. 71. So dividing that on both sides, 72271. So this divided by 0.72271. We get x ends up being equal to negative 5.92777. Right, so a ton of work to sit there and get to that answer. Just being very careful on our calculator, but that is how you would actually arrive at that answer. This is another problem. You're actually going to end up solving this very much the same way there. So looking at this, I do see I got a few more problems here. What I think I'm going to do is I'm going to save some of these for part 2 because this video is getting a little bit longer than I wanted it to. So I'm going to let you stop here. I will make an optional part 2 for this video right now. So if you want to watch that, you'll see that posted as well. Thanks, guys. Have a good day.